Hello students, in the last lecture we have studied about the angle of declination or simply a declination. So it was the tilt of a needle. So the needle should align in the geographic north and south. Instead of that, in actual practice it aligned along a magnetic north-south. So it makes an angle of declination. This was our geographic meridian and this is your magnetic meridian. So the needle or a bar magnet, instead of aligning in a true north-south, it aligned in magnetic north-south direction because we assume that an imaginary bar magnet of Earth. So let us assume this is the imaginary bar magnet of the Earth inside, where this behave like a north pole and it behave like a south pole. This is an imaginary bar magnet. So we take the magnetic field lines originating from the magnetic south and magnetic north. So that was angle of declination. Now let us see the magnetic inclination or magnetic dip angle. Now see, this is the magnetic field lines originating from either you say a geographic south or a magnetic south, and it goes inside the earth, and inside the earth it is opposite, that is from magnetic north to magnetic south. Now this magnetic field lines are not straight, it is a curve similar to a bar magnet. So we have seen this is earth, this is rotating about its own axis. This white strips are assumed to be the magnetic field lines. So clearly it is curved. So this is the axis of the rotation passing through the center, and we have this as a declination. Now the field lines are taken as these strips. Now suppose we are on the equator, so this is a place on the equator. All the place on the surface of the earth should be horizontal. It is not that if I move towards the pole, I will bend like this. So at every place, whether you are in India, America or Canada, the surface of the earth is assumed to be horizontal. The field lines are curved. So this curved lines or this strips, white strips, is assumed to be the magnetic field lines, that is curved. That is curved from south to north. Now when we are at the equator, suppose this is the equator. So let us say the point P is on the equator. Here we have assumed this is the earth. This is earth. So point P, we have taken different points. Points P, point X, and we have taken point P dash at the pole. So we have taken the different points to understand the dip angle. Now clearly when we are at the equator, when you are at the equator, the magnetic field line, it is along the tangent, so it will be straight. It will be straight. So what will be the angle of inclination? So angle of inclination is denoted by I. So at equator, first we understand about the equator and the pole. First we try to find out angle of inclination at equator and pole. So at this point or a place on the equator, the magnetic field line is along the tangent. So if I keep a needle here, this is the north of a needle, this is the south. It is redrawn here. So the magnetic field line is along the tangent. So it is like this. We have a earth. You are on this point, that is equatorial point, or this line is the equatorial line. So this is the magnetic field intensity along the tangent. Along the tangent, because the magnetic field line here is curved. So the dip angle is 0 at the equator. This diagram, so whatever is the place, you take this surface of the earth as a horizontal. We take this surface as a horizontal. So if you are on the earth at this point, this is its surface. It should be always horizontal. If you are on this place, this is horizontal. If you are on the pole, this is a horizontal. So these are the horizontal. So at any place, so if you are on an equatorial line, this is the horizontal. So horizontal and earth magnetic field are in the same direction. So that is redrawn. So this is a point on equator or equatorial line, and the same diagram is shown on this magnetic field lines, which is magnetic field lines are drawn on the magnetic meridian. So this is drawn from south to north. So this is south to north, magnetic south to magnetic north. This is the magnetic field lines curve. But when you are at the equator, where will be this equatorial point? This will be the equatorial point. This is the equatorial point. So it will be normal. It will be normal. Now, see, this is the situation. So BH, and this is the magnetic field line. So if I draw a magnetic meridian for an equator, this is the earth magnetic field. This point is equatorial point or a equatorial, the point lies on equatorial line. So BH, or this is the magnetic field intensity. In the book diagram, we have this as BE. This is true north. This is magnetic north. So this angle is angle of declination. If this is true north, this line can also be written as true east. That is perpendicular. 90 degree to it. So this line can be assumed to be true east. So this is the diagram in the book. We draw the meridian like this. So we take 90 degree to this true north as true east. So this can also be considered as a true east, that is perpendicular to the true north. Anyhow, when you are on the equator, now this is the diagram. So if I place my compass needle, it will get like this. Now I am moving towards pole. See the situation of the needle. This is needle. Assume this to be a north, this to be a south. So it is bending. It is pulled down. And at the pole, it becomes vertical. So we need a dip angle or a deep needle. The compass in our country is free to oscillate in a horizontal plate. It oscillates like this. We also need a dip angle to understand or to find out the dip angle. This magnetic needle should be able to oscillate in the vertical plane also, like this. So our needle oscillates like this, horizontal plane. It should align like this, true north, but in actual practice it aligns, so it shifts. That we have studied, that is a declination. Now, because the magnetic field line is curved, it will be moved up or down depending on the place. So see, dip angle is the angle up or down that the magnetic field of earth makes with the horizontal at a place. So at whatever place you are, we have to first draw a horizontal, and then you have to see the position of your bar magnet or needle. It will be pulled down when we move from equator to the pole. So simply you start keeping the needle on these field lines which we have drawn. So if I keep and you assume this as a north, so this is the situation, and at this place this is the horizontal circle. So dip angle is 0 degree. Then I am moving towards pole. So these are the field lines. See, the field line is bending. So needle is also bending. And at pole it becomes like this. So this is our north. It will be attracted inside the earth, behave like a south. Otherwise, let it be a magnetic north. And from this place, if you are moving downward, then your south will be attracted. It becomes vertical. It becomes vertical. So at point P, the dip angle is 0, and as I move from this point, let us take, you are moving on this line, the needle is bending down like this. So at point P dash, if I take here a point P dash, here point P dash, so this becomes its horizontal component. This becomes its horizontal component at the pole. And how is the needle? This is the south of the needle, this is the north of the needle. We extend this line in the downward direction. So how much angle it makes? 90 degree. This is your BH, this is your BV. Same thing is shown here, but we have changed the direction. So at the pole, the dip angle becomes 90 degree. So at poles, I is equal to 90 degree. Clear? This is the situation. So if this is a point at the equator, so if I move towards the pole, this is my pole, so it will bend down, 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 down like this. And if I move towards that side, it moves like this, and it becomes like this. So this is your BH, and this becomes your BV. In that case, you should draw BV in this direction. Sorry, BH in this direction and BV in the upward direction. So this is the situation. See this. So this is equator. So if it is not clear from this diagram, again I am drawing, you are on this point first. You have to see simply the magnetic field lines. This is your magnetic north, this is your magnetic south. Now if I am on this place, first I draw the horizon, and this is the magnetic field line, so it is along the tangent. Say what will be the angle? This is your BH, and this is the north of the needle, this is the south. The angle is 0, both lines are parallel. So I becomes 0, and I can draw the situation like this. Now come to the pole. So when you come to the pole, say this, it will be like this. This is the needle. So what will happen? Bend, 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 and then this is like this. So I take this direction. Now this is the horizontal surface of the surface at the pole, and this is the direction of the needle. So this becomes BV, and this becomes BH. So at the pole, this is BH, this is BY, and this is the position of your needle. So your needle north is at magnetic north. If you are at this position, so if you are on this position, so first you draw a horizon, then the magnetic field lines is radially outward. Now what will be the position of your needle? This is south. So here this will be the situation, this will be the south of needle, and this is north. And this point is your magnetic south. Inside its behavior is a north. So now this becomes horizontal and this becomes vertical. Now this is your BH, this is your BY, similar to this. So at poles, the angle of inclination is 90 degree. Now come to at any position in between. Come to the position in between the pole and the equator. Let us consider the point X. Let us consider a point X. So this is point X. So let us say this is point X. Let us draw the one magnetic field line only. This is the magnetic field line. So first we draw a horizontal. This is a horizontal. And what is the magnetic field intensity? It is curved. At this point, it is curved bendward. It is curved downward, sorry. It is curved downward. So I take up this vector. This will be your angle of inclination and this will be your vertical component and this will be your horizontal component. So take this vector, draw it here. So again you can easily see on this. This was the equator. When I move, the strips are bending downward. The strips are bending downward. So first we draw horizontal. First we draw horizontal. Horizontal will be drawn like straight line. But magnetic field, it will bend downward. So horizontal is straight. This is the horizontal surface. So at any place, if you are on any place, the surface will be horizontal. So first we draw horizontal, but this is the field line. See, field line is bent. So as I move from equator, see my fingers are bending. And then it becomes like this. So if I am at this position, this is the magnetic field line. Now, this will be the horizontal component and this will be the vertical component. So this angle will be called as dip angle, which was at equator, it was straight. Now it has bent like that. But your horizontal will remain same. Your horizontal will remain same. This is your horizontal. This is your vertical. And this is the magnetic field line. So what will happen at this point X? At this point X, if this is your BH, this will be your B vector and this is your BV, V for vertical. And this is called angle of inclination. So actually this is not a straight field line, it is bending towards the pole. So you are moving from this equatorial point. So at equator, the magnetic field line or tangent was straight. Now it is moving like this. So you have to draw a tangent. This is the tangent draw. An angle it makes with a horizontal is called angle of inclination. And when we come to the pole finally, it becomes 90 degree. So this magnetic field lines keep on bending and then this magnetic field lines come to B. That is like this, down. Then we take this as a down. So if this is a point at X, this is a place X, this is BH, this is the magnetic field line. This is your north of needle, this is the south of needle. And then again you draw and see this. This is now the condition of your needle. This is the north of needle, this is south. Now you draw this as V. And your bend B was along the y-axis. It becomes x-axis, negative axis. So BV, which was negative x-axis, becomes negative y-axis. Angle should be negative. So as we bend like this, the magnetic field is bending. So we have to change our components also. So clearly, now we come to this diagram. This is the Earth magnetic field. Now if you find any difficulty in this, just remember that this is the magnetic field line. We have drawn this on a magnetic meridian. This is the Earth resultant magnetic field. This is its horizontal component and this is its vertical component. The same diagram is redrawn in the book like this. So this is true north, this is SM. This BH is drawn like this. This is the BH. So BH, it should be perpendicular to BV. So here vertical component in the book is denoted by ZE and horizontal component is denoted by HE, E for Earth. And the resultant magnetic field is denoted by BE vector. It is two-dimensional. And The angle of inclination is this. The angle that the magnetic field of Earth makes with the horizontal at a place in the magnetic meridian is called as the dip angle. Now, let us resolve these components. Let us resolve this components. So, if we see the diagram, we can write, so at poles ZE is equal to BE. So this is your needle which is extended in the downward direction. And at any place, if this is any place, your needle will be like this, that is north-south. So we make this as BH and this as BB. Then this angle becomes angle of inclination. So as we are moving from equator to this, the dip angle is increasing, the needle is coming downward. So if you are at this point, the needle is along the tangent. At any point the magnetic field is along the tangent. At the pole it is 90 degree. In the book the diagram is like this. This is magnetic north, so that is HE, true north. This is angle of declination, BE and ZE. So there are two diagrams. This is easy to understand. So this is all about. So if you want to find out, you can also find out the magnetic field intensity of the Earth by squaring and adding this equation. So BE square. So individually you square this and that will be under root HE square plus ZE square, that is similar to the vector x component plus y component square under root will give the magnitude of the vector. So this is all about the magnetic dip angle and all about the earth magnetism. So we have three terms: the dip angle, angle of declination and horizontal component of earth. These are called the elements of earth magnetic field. They play an important role to determine the magnetic field intensity at any place. And one term is our this is the different formula. So if you want to find out the angle of inclination or magnetic inclination or magnetic dip, use this formula. If you want to find out the magnitude of the earth magnetic field, this is the earth magnetic field. BE is the resultant earth magnetic field. So this is all about the earth magnetism. Have a nice day.